Cool. So today's tutorial is about SLAM, and more specifically, we'll talk about SLAM, the backend of a SLAM system. And so since this is a tutorial, I was thinking maybe we should focus on the technical details, try to make the tutorial more solid. Of course, I will cover the high-level information about SLAM, high-level knowledge about models and the solvers, something like that. So here is what we are going to do today. I'll first cover the high-level model, then probably I will derive by hand to show the process of solving a SLAM, solving a factor graph system. And after this tutorial, we will start doing a practice. The practice has two parts. One is based on MATLAB, one is based on C++, in case somebody has already done the summer school 2 years ago by Shichao. So, okay, let's get started. And I believe everybody should have some understanding of the SLAM already. Well, SLAM is called simultaneous localization and mapping. It has two parts. One is localization, the other one is mapping. Well, the localization helps us to figure out where the robot is, meaning we are estimating the robot's position, robot's location. And for the mapping, the robot is trying to draw a map as it traverses through the environment. So down here, this is a typical paradigm of a autonomous system. From the sensor data is fed into a SLAM system. Then this system will compute the robot pose, figure out where the robot is, and also draw a map of the environment. The map can be used by, for example, a planning module. The planning module will figure out what is the safe way to move the robot and send the plan to the control module. The control module then use the pose from SLAM system and the path or the target movement from the planning module to figure out what is the control inputs to my system so that robot can drive safely. So, and this is a very simple example to show what is a typical scenario. It's very straightforward, very basic. So let's say we have a robot, well, in 2D. Throughout this tutorial, we should always assume, I will always assume we are dealing with a 2D robot moving around and observing landmarks. So we have a 2D robot moving around on the ground. And the robot, each time the robot can observe some landmarks. And we call those observations as measurements. Right here, the blue stars are the measurements from this frame. And as the robot moves, as shown by the black arrow, that is a odometry. Odometry information may come from the odometer sensor on the robot. It's basically tells you what's the motion, relative motion between the two frames. So at a new frame, the robot makes another observation. And right here, it sees the same 3 landmarks. And in total, because right now we have 6 blue stars here. And that means we have 6 observations in total. And the robot keeps moving. It will observe new landmarks, making new measurements. And also it may observe the old landmark shared by the previous frames. And eventually when the robot finishes the traversing, and what we get from this is a set of measurements. We know the frames that are observing the landmarks, but for the robot, it doesn't know where it is exactly. And that is what a SLAM problem is trying to solve. So that's why people also say SLAM is also a estimation problem. That's because we're trying to figure out where is the robot and where are the landmarks based on the robot observations. Okay, so right here we're showing a graphical model called factor graph, and that is a very popular representation of a SLAM problem. I'm not saying this is the only representation. It's just it's more modern, and it's very popular among the SLAM community, and it's very powerful too. So again, about the factor graph, first thing, it is a graph. And from this graph, we can see it has node as the post node as shown by the purple circle, and another different kind of node as shown by the green node. So this one is a robot pose. The node encodes the robot pose, and the blue node encodes the landmark position. So right here, we have two different types of nodes. And as to edges, depending on what kind of nodes the edge is connecting, we can have two different types of edges here. And for example, if the edge is connecting to post node, and this is corresponding to the odometry measurement, because odometry information tells us what is the relative motion between the two frames. So this is the odometry measurement. And the other edge, the other type of edge is called the landmark measurement, because it's connecting a robot and a landmark. It means a robot, this edge means the robot here at this frame is observing the L1 landmark. So that's a connection. And as to why this graph is called a factor graph, that's just a new name people figure out to call the edges here, because we have different types of edges, or we can say we have different types of factors. So yeah, you may, okay, so one more thing. You may also notice there's another different type of edge, which is only connecting to the first node. Well, so this node is not a real measurement, unlike the other connections. Other connections are all measurements from the robot. This one is not a measurement. It's just a way we want to fix the position of the first node, the pose of the first node of the robot, the first frame of the robot. So yeah, that's all about the factor graph. And how do we do estimation on the factor graph? So remember what we are given, and we are given a set of measurements between robot frame or between a robot and a landmark. We are given the edges. And our goal is to figure out what is the state of my robot poses and the state of the landmark, meaning the landmark positions. So if we model this to be an optimization problem, what we are trying to optimize is the difference between our predicted measurements given the state, which are unknown, between the predicted measurements and its difference to the real measurements. We want to minimize the difference between them. So to figure out what is the predicted measurements, we need the state here, which is the nonlinear function. Given the state, we can go through a nonlinear function and figure out what is the predicted measurement. Let's use an example to understand it better. Let's say we want to predict the measurement between those two robot frames. What we can do is we just compute the relative motion using the robot pose at x0 and the robot pose at x1, and compare that with the measurement. Remember, the measurement is also a relative motion. So the error is defined by the difference between those two different motions, different relative motions. And again, our goal here is to estimate a state x, which best explains the measurements. So one more thing I want to clarify here is the index here. We see Z1, Z2 until Zn. And this index means the index of a measurement. If we have 1,000 measurements, then n is 1,000. It doesn't mean the index for a state. It's not x0 to xn. Okay. All right, that's it from the high level optimization. And let's see how we define the difference. So the first thing to define difference is to define the error function. This error function actually models what is the difference between our prediction or our measurement. So let's say our prediction is Fi given the hidden state x, and our measurement is Zi here. And this again, this index here means the index for measurement. And for each measurement, we can define an error function called Ei. So x here is a state vector, and it contains the robot poses and landmark positions. Let's take a closer look at what is x, the state vector here. Can you guys see my notes now?
Yes.
Okay, cool. So let's say we are solving a 2D case, and the pose of a robot, let's say xi, which is a vector, contains the x position, y position, and the angle theta, and we give it an index. So that is a pose for a 2D robot. And as to our state vector, that is a long vector stacking all the poses together. So this is x1, the pose for the first frame, and x2 pose for the second, all the way to the pose for n. And if we have landmarks in the states, we also want to stack the landmark positions. Let's say a landmark position is x and y. There's no heading information for landmark. In 2D, we assume that's a point. We only need x, y to define a point. So this state vector will keep growing from xn plus 1, xn plus 2, all the way to xn plus m. So the first n is a n poses, and the last m is m landmarks. So this is our state vector here. All right, go back to our slide. So let's again look at this error function. We have a measurement here. That is what we get from the sensor data. And we have a measurement model to predict what is the measurement based on our state vector. And we can, about this measurement, because it's a data we captured from the sensor, it will never be perfect. So that is why we want to assume a distribution of this error term. In an ideal case, this error term should be 0 if our estimation X is correct. But in reality, because our measurement is noisy, this error term will never be 0. Well, it's very unlikely to be 0. So that's why we assume a distribution. And specifically, we assume a zero mean Gaussian distribution. And we use a covariance matrix, or you can also call that information matrix, to model this Gaussian. So in the end, we can compute the least square of this error term, which is EIX transpose multiplied by the information matrix, which is a weighting term here, and EIX. So this is the least square term, and well, it's unlike a normal L2 norm. We have a weighting matrix, which is an information matrix for the measurement, for the sensor measurements. And one question is why people are always using least square. You must have seen many people formulating problems using least square, trying to minimize the least square error. And why is that? The reason is, if we assume the error term here is actually a Gaussian, doing a least square minimization is equivalent to doing a likelihood maximization. So probabilistically speaking, we are doing the optimal thing here by using a least square. So yeah, that's just one fun fact to know. So another thing about this least square term, we have this error function. And this error function is usually a vector. But the least square, the squared error of measurement, is always a scalar. And remember, we derive one squared error for one measurement. That is why we have the same index I here. So then we can talk about how what we are doing by saying optimizing a postgraph. Well, optimizing a postgraph is actually optimizing a cost function of f. The capital F here is actually a sum of all the squared errors we just discussed before. And one thing I want to point out that because the error function may not be linear, and also we are using a L2 norm here, the f function, the total function, is not linear, or it's not quadratic, and the point is it's not in a form that can be easily solved. And so now let's recap what is the overall SLAM system looks like. We have covered what is a postgraph and what we mean by optimizing postgraph. It's just trying to minimize the sum of error. So in a typical SLAM system, we divide a system into front end and back end. For front end, the main job is trying to construct this graph by figuring out what is the relative motion and which landmark the robot is currently observing, something like that. It's trying to figure out what are the edges of the graph. Then for the backend, given all those edges, we try to run this graph minimization error minimization or graph optimization thing to optimize our hidden state X. And again, the graph optimization is trying to minimize this sum of least square error. And you may have heard about using different methods such as filtering, bundle adjustment, or different solver libraries like ISAM, series, GTSAM, GTO, something like that. But the thing is, they are just different tools try to help you solve this same cost function. And in this tutorial, I'll only focus on how to optimize the given cost function. Now let's see what are the methods to minimize a cost function that looks like this. So our goal is trying to find a optimal hidden state that minimizes sum of least squares. And typical methods include Gauss-newton or Levenberger-Marquardt method. And even though they are different names, they have different names, but the key idea here is trying to do a iterative linearization. So I guess that's the time I can switch to my notes. Let's try to try to use the derivation by hand to show what is a Gauss-newton method, why it's called the iterative linearization. Okay, let me switch to my notes. Okay, so remember we have this optimization problem, which is trying to find optimal X given a cost function. Oh, by the way, you're welcome to look at the following slides because what I'm doing right here is covered by the following maybe 3 or 4 slides, just to help you to catch up if you miss anything. So we know this is a nonlinear function. And the way we typically solve a nonlinear function minimization is to switch a problem a little bit. And usually for this kind of problem, we start from a initial guess. Let's say the initial guess is x0. And to switch a problem to another way so that we can better understand the linearization, we now, instead of trying to find an x, we try to find a delta x. The delta x is the difference of my current estimation, which is the initial guess. Oh, sorry. From the optimal solution. So this delta x here basically models how far away right now from the optimal solution, which is x star. So if we model the problem with delta x, then now the optimization problem is we want to find a delta x, an optimal delta x that will minimize this function. So this optimization cost function is basically says how far, what's a step we should make to reach the optimal solution. So please be noted that we haven't done any linearization yet. we just switch the problem from trying to find optimal x to trying to find what is the optimal step x should do to reach the optimal solution. Okay, so now because we know fx is a sum of the error of x transpose and information x, the error function here. Because we know this, let's just replace x with our new variable here. This is sum of over I, error function I, then x plus delta x transpose information and error function I, x plus delta x. Okay, so now look at the cost function. We know this term is nonlinear, and that is where the linearization happens. Let's take out the EI here. Let's try to linearize it around the initial guess x. So this is a nonlinear. And by applying the first order Tyler expansion, we can say this EI x0 plus the partial of EI x over partial of x at the point of x0 multiplied by delta x. Well, what we are doing right now is using the first order Tyler expansion to get another expression of EI. EI, the error function, is nonlinear, but right here, this is linear. By saying linear, we say it's linear with respect to delta x here, because this term has nothing to do with delta x, and this term also has nothing to do with delta x. So it's a linear term in terms of delta x. Okay, so if we, for simplicity, we just call EIX here as EI, and this partial derivative, we call that Jacobian JI. So now the error function becomes EI plus JI delta x. And we put this expression back to here and get delta x star equals to minimizing over delta x, trying to find sum over I. This is EI plus JI delta x, of course, transpose, and my information matrix. Then another EI plus JI delta x. So let's keep doing to find what is this function. What is this function is doing with respect to delta x? So right here, this is EI information matrix EI. We have EI transpose information EI, and the EI information JI delta x plus EI information matrix and the JI delta x. And JI delta x information and EI, that is the same with this term. So we just put a 2 in front of it. And finally, we have JI delta x, JI delta x. That is delta x transpose
then JI transpose, then information matrix JI dirt X. That's it. And also, if we want to further simplify this expression, we can put the sum, put a sum symbol into those terms. So, well, the first term will just be sum over EI. And the second term is sum over EI information matrix JI dirt X. The third term is dirt X transpose sum over I JI transpose information JI, then dirt X. Okay. All right, cool. So right now, let's see. We can rename it. Okay, let's first rename the term within the sum. Let's say this is because this is a constant. There's nothing to do with dirt X. Let's say this is CI, and the whole term is C. So C is the sum of CI. And then for this one, we say this is vector BI, BI transpose. And then the sum of BI transpose is B. So the B here, this is actually a vector. And C here, this is a scalar. And similarly for the inner term, we rename it to HI. And the whole summation term, we rename it to H. H is the sum of a single HI. So right now we can have a much simpler expression of the cost function, which is C plus 2B transpose dirt X plus dirt X transpose H dirt X. And this is a quadratic function. So now that seems like a good news, right? Because for quadratic function, if we want to minimize it, what do? We just take the derivative and set it to 0. So let's see what happens if we derive the derivative. The derivative of this whole term with respect to dirt X, this whole term is our cost function. Should be go here. And then we get 2B transpose plus, okay, transpose H. Or we can just do the transpose. This is 2B plus H dirt X. Oh, sorry, there should be a 2 because we are using the quadratic term. The derivative of that should have a 2 here. Okay, we set this derivative to be 0. And what is the X? We can just do, okay, this is H inverse B, and there should be a minus here. So essentially, to minimize a quadratic cost function, we are actually solving a linear system, which is H dirt X equals to minus B. this is a linear system we are solving now. So let's see what we are doing here. We start from a nonlinear cost function and ended up with a quadratic form of it. So this quadratic form is approximation of the original nonlinear function. And to solve this quadratic form, we just solve this linear system here. So this is one of the most important conclusions of today. So solving a nonlinear function, by linearizing it, we get a quadratic form. And to solve the quadratic form, that is equal to say we want to solve this linear system. Okay, so yeah, that's it. Let's see one more thing. Let's see what is the intuition of doing the linearization here. Let me draw a curve. Say we have this is our fx, which is a nonlinear function. And we want to find what is the optimal solution of x to minimize the f. And we start from some point. This is the x0. So by doing this linearization, we get this quadratic form here. That is doing a local approximation using a quadratic function. So essentially, we're using this quadratic function. Let's say that's qx. Using this quadratic function to locally approximate this part of the original nonlinear function. That's what we are doing right now. So when we solve it, when we solve the quadratic function, we find what is the delta x here. And that will move us to a new estimation, x1. Let's say this is x1. And from x1, we can make another approximation. Let me choose a different color. Sorry, this is supposed to be another quadratic. So, and so by solving that quadratic function, we get a third. This is x2. So you see what is going, right? This is what we call iterative linearization. So each time, starting from x0, we do this linearization thing to find what is the optimal delta x. Let's say, because this delta x is obtained from x0, we say this is delta x0, the optimal solution. Then we update our x by x0 plus delta x0, the optimal. We say this is x1. Then given x1, we do another linearization here. Get a second optimal delta x0. Oh, this should be 1. Then do a second update to get x2 equals to x1 plus delta x1, the optimal. And if we repeat that until delta x, the optimal delta x is really small. So that is what we call the convergence. And till then, hopefully, we will come to this optimal solution overall. So that is the idea of iterative linearization, or we call it Gauss-newton method to solve this least square problem. Okay, so far Are there any questions? Well, if not, I will just move on, go back to the slides. Okay. So it seems like we have found a solution to solve this nonlinear least square minimization problem. And this slide is just repeating what I have done. So we have this. Okay, we have this linear system here. That is one of the most important. We say that's one of the most important conclusion we can do today. Solving a nonlinear is equivalent to solve this linear system iteratively. And this is a typical step to do a Gauss-newton method. We have this error function and do the linearization to get EI plus JI delta X, and then construct the B vector and also the H matrix. And once we construct the linear system, we can solve it by doing the inverse. For now, well, the thing is, doing the inverse sometimes is very expensive, especially when the dimension is very high. But for now, don't worry about it. We can always do, if we don't care about the time, we can always do an inverse here to solve this linear system. And once we solve optimal X, we can do the update. Okay, that's it for that's all about the iterative linearization thing. And from here, let's take a closer look at the Jacobians, because before we say we use the term Ji to illustrate the Jacobian. Oh, sorry, it's not third heads. To illustrate the Jacobian, but we haven't shown what is actually the Jacobian here. So let's go back to our notes. A closer look at Jacobian. Let's say we're dealing with EIX, the error term here. So remember the state vector we just shown before. The state vector contains x1 vector, x2, all the way to xn plus m. This is our state vector. But what is a EI here? What is EI modeling here? Let's recap what we got from the vector graph. So we have a connection here, connection here. So let's say our EI models the error term of this relative motion measurements. So it's essentially, let's say this is xi, xj. So one thing I should clarify is that this I term here is not equal to this I. This I is the index of measurement. And this I is the index of index of nodes, let's say. Well, to avoid more confusion, let's just say this error term is Eij, because this error term is really about xi and xj, and it has nothing to do with the rest terms. For example, this xk here, it doesn't contain any term of xk inside it. So we can actually say this error term is xi, the vector, and xj. Okay, so now this ij becomes the index of our measurement. Because our measurement is always a measurement between two nodes, either post to post or post to landmark. So this ij here is our index for error term. And our input here becomes xi and xj. So to derive the Jacobian, let's see. Now the Jacobian is the error term ij over the whole state vector. But we know this error term is only related to xi and xj. We know that Eij ij over x2 and all the way to Eij over xi. And then Eij over xj, and all the way to the end. Because we know this Eij, the error term, is only related to xi and xj, we know that only those two terms are non-zero. All the other terms are all zeros in between. So that is why we say this Jacobian matrix is a sparse matrix, because we only have two terms, or to be more precise, we only have two blocks. This is non-zero. Zero, 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 all the way to Eij, xi, and Eij, xj. So that is the structure of the sparse Jacobian. And go back to our slide. And so as shown here, this Jacobian, just as what we have shown before, this Jacobian is sparse. Only the block related to xi and the block related to xj are non-zero. All the rest elements are zeros. And we further define this non-zero term, the non-zero term related to xi to be aij, the non-zero term related to xj to be bij. That's just a renaming. Okay, let's move on. So remember before, when we derive the iterative linearization, we say optimizing the cost function, nonlinear cost function, is actually trying to solve a linear system iteratively. And to construct this linear system, we need this B vector, and also there's another one, this H matrix, the B vector here, and this H matrix. So those two terms are actually related to our Jacobian here. Because our Jacobian is sparse, has a sparse structure, we want to investigate what is the structure of our linear system, the B term and also the H matrix. So for B term, we can see that the Jacobian transpose has two non-zero elements, non-zero blocks. This is a block related to Xi. This is a block related to Xj. And our information matrix, well, that is a dense block. The information matrix, if we want to use an example to show its size, let's say we're dealing with a 2D example where each Xi is Xi, each measurement is Xi, Xj, Yi, and Zi. These are measurement. So then this information matrix should be a 3 by 3. And our Jacobian is a n multiplied by m by 3. Okay, and this error term here, this is also a dense vector, but luckily a very short dense vector. This is 3 by 1. So eventually we have a long sparse vector of size n times m by 1. So this is the Bij, what Bij looks like. And remember, what is the B vector? The B vector is just a sum, sum for all the ij of Bij. So, okay, sorry. Let's not worry about this for now. Let's only focus on the Bij here. Oops. And the Bij right here is just the exact form of what Bij looks like. Again, it's a long vector. Only 2 blocks are non-zero. This is a block related to Xi. This is a block related to Xj. And as to Hij is here. This is Hij. And Hij has a form of Jacobian transpose multiplied by information matrix and then Jacobian. And if we do that multiplication, we get a matrix. This matrix is n times m. Remember, n is a number of poses, m is a number of landmarks, times n times m. So this is the size of this matrix. But luckily, because our J has this structure, a sparse structure here, the resulted H matrix is also sparse. Well, the good thing about sparsity is that if we want to store this matrix in memory, if we want to store the complete matrix, the dense matrix, it will cost so much memory. And for example, if you're using an eigenmatrix and define a square matrix of size, let's say 100,000, and each element is a double type, and the resulting memory it costs for a single matrix of size 100,000 is about 70. It's more than 70 gigabytes. So that's too much. That is why we want to investigate what is the sparsity of this matrix, so that we can only pay attention to this non-zero terms instead of the whole matrix. So again, down here, This is the formulation of what the Hij matrix looks like. In here, only 4 non-zero blocks corresponding to the 4 blocks here. Okay. Yeah, I think that's it. So now we have Bij and Hij. To actually get the linear system, which is H delta X equals minus B, we want the B, we want the H. And what is B, what is H? It's right here. It's simply sum over all the single B vectors. And for H, it's a sum over all the single H matrices. Yeah, that's what it is. So to look at the structure, if we sum over all the Bij, this is B, for example, 1, 1, B, 1, 2. If we sum over, oh, to be more precise, maybe this is X2. Let's say this is X6. This is 2, 6. And this is X1, this is X7, and this is 1, 7. So the idea is if we sum all the single B vectors together, we actually have a dense vector. That's because all the terms, all terms of xi from 0, sorry, I from 0 to n multiplied by m. All the terms are covered by those B vectors. And if we look at the H matrix here, we sum over all the different Hij. This is H26. This is H17. We sum over them and get this. This is also sparse matrix. This is our H matrix. So as you can see, this is a symmetric matrix, and also only some of its blocks are non-zero, and most of those blocks will be zeros. So when solving this linear system, and we talk about sparsity, what we mean is really the sparsity about this H matrix. Because right now we don't have to save the whole matrix into the system, but only save those non-zero blocks. Okay. All right, so this slide is nothing new. It's just a recap of what we have done so far. For each measurement, we can derive the error term. And for the error term, we can derive its Jacobian, and we know the Jacobian is sparse. Only two terms, one term related to xi, and the other term related to xj are non-zero. And this is how the Jacobian looks like. This is a sparse j. Then we can compute, based on this Aij, Bij, we can compute the B vector by simply updating the B vector by all the Bij's. This is Bij. And also for the H matrix, we simply update the four different non-zero terms of the H matrix. Those 4 different terms are II, Ij, this is Ji, and this is JJ. So we are updating those four non-zero blocks. Okay, so now where are we? We have covered how to do the linearization to build the linear system, trying to solve h delta x equals to minus b. This is a linearization system. And we also have figured out how to efficiently, well, both memory-wise and also the computation time-wise, we can efficiently compute this H matrix here. So then the next thing is to solve this linear system. Once we solve it, we can update the X, and we iterate this process until it's converged. That is the optimization algorithm we have covered so far. Okay, so now the question is, we say we can solve this linear system, but by using the inverse, thing. Should be minus. But in reality, we can do much better than doing a direct inverse. So this is a step that we use matrix decomposition. And because the reason why we can do this efficiently is because the very special structure of H matrix here. H matrix here, this is the symmetric matrix. So for symmetric matrix, we can do different types of factorization. For example, Cholesky or QR decomposition to help us efficiently solve this linear system. And in here, let's use Cholesky decomposition as an example to show how you can efficiently solve this linear system. Let's say we are given a linear system like this, and A here is very special. It's symmetric and positive definite, just as our H. Our H is also a symmetric and positive definite matrix. So what Cholesky decomposition does is it can decompose A into two matrices. It's actually one matrix, this lower triangular matrix. By lower triangular, we mean this arrow matrix only has values here, arrow ij, and all the rest, the upper triangle, the upper triangular will be 0. So if we can do this decomposition, now the linear system becomes this. We can solve this y vector here first, because this is lower triangular. Arrow matrix is lower triangular. We can solve it quickly by doing variable substitution, starting from this first element. And once we solve y, we can do another. Similarly, we can solve this second linear system, but here this is the upper triangular. So now it looks like this, and the lower triangular is 0. This is our x equals b. So in this case, we start from the last element. We solve it and solve the rest by substituting, by taking the first one into them. So that's the idea of solving a linear system using Cholesky decomposition. And the point is, by using this decomposition method, we can solve a linear system much more efficiently than doing the direct inverse. Okay. So let's see what we have covered so far. So we have shown how to do a linearization of this nonlinear cost function. And by iteratively linearize that, we can solve a least square problem. And we also show how to build this right here. We also show how to build this linear system here, and using the sparsity structure to do that efficiently. And the last thing we have shown is how to solve this linear system efficiently by using matrix decomposition. So seems like we have covered all, except one thing. That is, we haven't covered what is the error term. How to define an error between poses and between pose and landmark here. So before doing that, I suggest we do a 5-minute break. And then we start from slide 29 to introduce how we formulate the pose to pose constraint and pose to landmark constraint, and how to derive the Jacobian of that. Okay, so let's just recall what we have covered so far. We have covered how to formulate a nonlinear least square given a pose graph. Given the measurements from the robot, we can formulate a least square. And we introduced how to linearize this nonlinear least square function. And we also introduced how to build the linear system to iteratively solve the nonlinear problem. And so for the second half, I will introduce how to define the error, the measurement error, and how to derive the Jacobian of that. The second part is also covered in the guidance, which I will send to you later. That will be very helpful for your practice problem. But now let's focus on the slides. So remember, when we talk about pose graph, we say we have two different types of vectors or different types of measurements. One is the measurement in between different poses, like here, like U1 here. The other is the M, is between pose and a landmark, robot pose and landmark. So for the first one, pose to pose measurement, what we observe is actually a relative motion. And our prediction based on the x0 and x1 here is computing the difference between the two poses and compare the difference to our measurement. That is how we define the error between pose to pose. And for the other one, pose to landmark, we define the error as what is the local position, what is the position of a landmark in the local frame of this robot here, and compare that with the measurement, because the measurement is a measurement of the landmark in the local frame of the robot. So now let's see it more formally. So in here, and also in the practice problem later, we define the pose of a robot to be a 2D pose, which contains xi, yi, and theta I. And we define the position of a 2D landmark to be XL and YL. So to formulate the pose-to-pose measurement, we first clarify for the pose 1, which is xi here, we have a translation vector. This is a 2D vector. And we also have a scalar here indicating the angle of xi. For xj, that's basically the same thing. And for the measurement, because we know the measurement is a relative pose, we can also use a 2D pose to parameterize the measurement. So this is the translation vector between ij. And this is the heading angle difference between ij. And just a little more about the kinematics here. We can convert a pose vector. This is a, let me use my pencil here. In here, x is a, say x here, this is a vector. We know we can convert a pose vector into a transformation matrix. This is a transform. And we note this transform as a capital X here. So lowercase denotes vector, and uppercase denotes a transform matrix. And inside this transform matrix, we have a rotation matrix, 2x2 rotation matrix, computed from the angle, and a 2x1 translation vector computed from xi and yi. And also we can do the inverse thing. Given a transform matrix, we can convert that back into a vector. So given those preliminaries on kinematics, we can now compute what is the error between our prediction and the measurement. So this part, which is xi inverse multiplied by xj, this is computing the difference. This is our prediction. By multiplying the inverse of our measurement here with our prediction, this is a total error in matrix form. Then we compute, we change the matrix back into vector using this function, transform to vector. So this is eventually we have a 3x1 vector to denote our error. This is our error function. And how does that happen? So we know for x1, for xi, we have a transform matrix like this. For xj, we have another transform like this. And by multiplying the inverse of xi, this is the inverse form of xi transform, we get the matrix form error difference. This is a transform of relative motion. And also this is our prediction. And we can convert this prediction transform back into a vector. And then the error term here is just doing a measurement inverse multiplied by this matrix here. In reality, so this is a pose-to-pose error. For translation, this is translation. If you finish the matrix multiplication, you will get a formulation looks like this. It's related to Ti, Tj, Tij and also the rotation of Ri and Rij. And the third term here, this is a rotation. And for rotation, because we are dealing with a 2D robot, we only care about the heading angle. So the heading angle difference is the difference of the two robot heading minus our measurement. This is a measurement. This is the prediction. So again, this is a 3x1 vector. And remember, when we try to compute the Jacobian and try to construct a linear system, we are actually computing the A and B blocks here. For blocks A, remember we're computing the derivative of Eij over Xi because A is related to Xi. And for B, which is related to Xj, we compute the derivative over Xj. So let's see. Let's see if we can derive this Aij, Bij here. Okay, what we are given is Eij, which equals to a delta t and a delta theta. This is a 3x1 vector. And for delta t, from the slides, let me see. We have a formulation of Rij transpose Rj, sorry, this should be Ri transpose Tj minus Ti and minus Tij and here. And for the theta, we have theta j minus theta I minus theta ij. This is just copying what we have shown on the slides. And for Aij, we have Eij over Xi. Remember, Xi is Ti theta I. So from here, since the error function, this is a vector, and also the state of pose I is also a vector. So when we compute the derivative, we essentially are computing a matrix. This is partial of delta t is here, over Ti. And on the right, this is delta t over theta I. Down here, this is delta theta over Ti. And here, this is delta theta over theta I. Okay, now let's look at them one by one. Delta t is this. Delta t over Ti, we can see Ti is happening here. So it's straightforward to say the derivative is Rij transpose Ri transpose and then minus 1. So the second term, delta t over theta I, this is delta t over theta I because the theta I is related to this Ri here. So we compute the derivative as Rij, which is a measurement, and Ri transpose over theta I. And then multiplied by the distance of translation. That's it. For the third term here, this is delta theta. Delta theta is here. Delta theta over Ti, because there's no Ti. we put 0. Then the final term, delta theta over theta I. We know there's one theta I here, and this is -1. And similarly, for Bij, we have the same thing. I won't derive it here, but now you get the idea. We simply construct this Jacobian matrix and solve the term one by one. Let's go back to the slides now. So this is what we got for the Aij. And we have shown how to derive that. And for Bij, it's basically the same. And right here, this derivative of a rotation matrix can be simply done by taking the derivative of each element. So the derivative of a rotation matrix over the theta here, you will get a matrix as a derivative. So now we should know how to compute Aij and Bij. Using this Aij, Bij, we can construct the Jacobian matrix. Then from the Jacobian, we can construct what is B, what is H. And from that, we can solve what is delta X. Okay. And very similarly for pose to landmark, we define the pose to be a translation vector plus the angle, and define the landmark positions to be XL and YL, and define the observation from a pose I to landmark L to be a position. This is a position in the local frame of the robot. So now our error function is, we want to first, our error function is shown as in this equation. What we are doing here is we first transform the XL here. Remember, XL is the landmark in global frame. We transform landmark in global frame back into landmark in the robot frame. So this is landmark in robot frame. And in robot frame, we can compare the landmark position to what we have observed. So this is a measurement in robot frame. So by taking the difference, we get the error function. And for this error function, this is a 2x1 vector. And again, we can do a similar thing. Given this expression of error function, we can compute AIL, BIL, and doing the same derivation to get what is A, what is B. Then from A and B, we construct J, and from J, we construct B and H. And from that, we solve what is delta. Oops. So yeah, that's it. So all those materials about pose-to-pose and pose-to-landmark measurement, how we define the error function, how we define the block A and block B, is all covered in the MATLAB practice handout. And okay, now let's move on to the coding session. Are there any questions so far? Okay, good. Okay, let's see. I have already shared this tutorial, this slides on Slack in the notification this morning. And this is about how you want to solve this practice problem. So the practice questions include two parts. One is based on MATLAB. And this is the MATLAB practice problem is the same as 2 years ago. And if you feel you have already done that, or you feel you are confident about the theory, you can move on to the second part, which is based on C++ using series and GTSM to solve a postgraph. So for the first part, in the MATLAB example, it's trying to solve a 2D SLAM problem. And you'll be given 2 files, actually 3, including the solution. The first one is a practice. It will include a set of MATLAB code. And what you want to do is look for the least square SLAM, this script, to look for the to-do marks. And under to-do, you want to fill in your own code to complete the function. And when you look at the least square SLAM, the script, you want to find what functions it calls and try to investigate those functions, because those functions may not be complete. You want to complete those functions, then complete the main function. Once you finished, you can run this main script to see the results. And in here, this is a guidance or write-up specifically for the MATLAB code. You can see what the MATLAB code is doing and what each folder contains. And you can see the expected results for you to debug. And also, here are some hints and also theories we have covered in our own tutorial. Yeah, those should be used for a reference. Will be very helpful to help you solve the problem. And also you can check this solution package here. It's the same package, but with all the functions being complete. So that's it for the first part. For the second part, it's mainly using series to solve a 3D SLAM problem, 3D postgraph problem. So in here, I say no Jacobian needed. That's because series is a very nice library that can formulate the Jacobian for you once you have defined the error term. So what you want is to check out the setup guide here. You want to install a Docker image following this guide. And inside this Docker image, it has already a, sorry, are there a question? No, okay. Inside this Docker image, you'll find the GTSM and the series is already installed. And it also has a SLAM workspace setup. And you can do catkin inside this SLAM workspace, but right now there's no code in it. So to use this Docker image, you want to start a Docker container. So the simplest way to start a container is doing this command. But more practically, you want to link your folder, one of your local folder, to this container using this command. For example, right here, I'm linking my local documents folder to the path, to this path inside this container. So for the actual package, you want to check out the SLAM tutorial, which is on our GitHub repository. And if you already done so, you may want to do a git pull again, just to make sure you have the latest version. So checking out the package you have 2 options. Option 1, you can check out directly from inside a container, but this is not recommended. A better way is to check out onto your local machine and link the directory to the container. For example, I check out the SLAM tutorial into the code directory here. And then I link this code directory, then SLAM tutorial, to a directory in the container. The directory is inside this SLAM workspace. And inside the source directory, it's called the SLAM tutorial. So that when you compile it, when you compile the SLAM workspace, it will compile the local code on your local machine. Okay, so yeah, once that's done, you want to do a cat make to make sure everything compiles correctly. And yeah, that is what you want to do with a compilation. So about this repository, if you check out the master branch, that contains code that's not complete. You want to fill in the code following the comments inside the code. And if you want to do a quick demo, you can also check out the solution branch and just do catkin and ROS run. You can get the result. So for the code, we basically have two executable. One is using series to solve a sparse postgraph, and the other one is using GTSAM. For the first one, this is a main practice problem, and it has two code blocks to be filled, marked by to do, and you want to read through the code to make sure you understand what is going on. And for the GTSAM, it's demonstrating a very simple example of a postgraph. And so this is example, it's not a problem to solve. The goal is for you to provide a template in your future. If you want to use GTSAM, this could be a minimal example. And for the data set is given as CSV text files. You are given two text files. One is initial poses, the other one is constraints. The initial poses contains what is the camera ID and what is the initial guess of my camera pose. And the constraints, the constraints contains two cameras, contains two camera ID and the relative transform between two cameras. So for the transform, in here we use quaterny and translation vector. So in total, you are given 7 numbers for a transform. And as to the data IO, you don't have to worry about it. It's already implemented. It will read in the text file and formulate that into a standard C++ container, vector container. And from that, it should be very easy to use. For output, the code will generate results to the specified directory, and you don't have to worry about it. Once you have do the ROS run, get a result, simply open MATLAB and run the script visualize results. It will show you what the initial guess looks like and what the optimized poses looks like. Okay, and I think that's it. We spent almost 2 hours talking about how to formulate and solve a postgraph and introduce the practice problem. I highly recommend to do the first one if you haven't done so. This is very interesting to help you understand each single step, how to compute the Jacobian, how to construct the linear system and do the linearization. This is very, very useful to understand a SLAM system. Okay, I think then that's it.
Hi, Wei-Kun.
Yep.
Actually, I have a question about theory.
Okay.
So I'm a little confused where we can get the information matrix or covariance matrix.
Okay, yeah. So let me see. And you keep. Let's go back to the definition. Where is my pencil? Okay, right here. So this information matrix here, well, it's usually tuned by hand, or in my experience, it's usually tuned by hand. You can either give it as like this sigma x, sigma y, or sigma z square. Oh, sorry, there shouldn't be sigma z. There should be sigma theta. So this is usually what I do. I assume how much I trust about the measurement, then I give it a sigma x as the as a number to model to what extent I trust my sensor measurement. If I really trust my sensor data, this number is small. It has small covariance. And if my sensor is very noisy, then this should be big. So usually this is how I specify the covariance matrix. And for simplicity, you can also do a identity matrix here in the simplest case. So yeah, I don't think you will have to worry about the information matrix, how to define that in the practice example. But right, in reality, you will always have to deal with this kind of stuff. And usually it's tuned by hand. Sometimes you can compute that from front-end pipeline. For example, for VIO, we can use the number of tracked features for each frame to estimate how much we trust the post estimation.
Thanks. Okay, thanks.
Yep. So if you guys have no more questions, you can go ahead, start to download, to set up, and try to start working on the MATLAB problem. Then I will keep this tutorial Zoom session open in case you have any question. You're also welcome to message me on Slack. And
hey, Wickham.
Yep.
I cannot access the GitHub repository. It doesn't seem.
Yeah, you have to log in first.
No, but with which email? I don't know if my email particularly, maybe it's not.
Which one is associated to the AirLab GitHub? The CA
That's a good question. I'm gonna try to find that out now.
Okay. Okay. I don't know if I should make the repository public. Let me see.